Hi, everyone. Karishma here. I am so glad that you're able to attend this session. So today, as Rochelle mentioned, the topic is why good math tools make engineering education even better. Just a little bit about my background. I studied electrical engineering, so I have a bachelor's degree of electrical engineering, and then I have a master's degree in biomedical engineering. And I have to say that as a student going through my engineering education, I struggled a lot with the math. I didn't really understand why I was doing the things that I was doing. I was just following a set of procedures and trying to keep my head above water. And so, why I'm really excited about this presentation and the things that we're doing at MapleSoft is, we're trying to make sure that engineering students are able to appreciate the mathematics and they're able to see how it connects to the topics that they're learning. So without further ado, let me get to my first slide. So mathematics has played a major role in bringing innovations to reality. I think all of us would agree about that. And many mathematical theories and models of real-world problems have helped scientists and engineers grapple with seemingly impossible tasks. Click, okay. So mathematics lies at the heart of all engineering, but it can be a blessing and a curse when it comes to engineering education. Truly understanding the underlying mathematics can lead to deeper understanding of fundamental engineering concepts, but the mechanics of the computations can also impede that understanding. And that is a struggle that I experienced as I was pursuing my undergraduate and graduate degrees. It's, you're so focused on the mechanics of the computation that you lose sight of understanding what the mathematics is trying to tell you. And so students get lost in the calculations. And so our goal is really to help students. We're passionate at MapleSoft, we're passionate about math and math education. And we want to provide educators as well as students with software tools that'll make it easier for them to understand and appreciate the mathematics that drives engineering phenomenon that they're studying. So in today's session, you will learn how a good math tool can improve engagement. So how it can keep students engaged with motivating examples and realistic applications that would otherwise be too difficult or too time-consuming to do by hand. How a good math tool can help students learn important concepts by relieving the burden of tedious, error-prone calculations that can prevent the student from focusing on what's the most important thing when learning the material. Good math tools can encourage experimentation and iterative designs by exploring the effects of changing parameters. Those what-if explorations, where the calculations or graphs are done and then the focus is on the analysis. And lastly, to instill understanding. So to increase student understanding with illuminating explanations and visualizations that help make the math and engineering concepts more tangible. So let's talk about this first point over here, the improving engagement. What we want to do as educators and in talking to educators, engineering educators, we want to keep students engaged with motivating examples and realistic applications, as I mentioned before, that would be too difficult or time-consuming to do by hand. So this is all about giving students that aha moment. So capturing their imagination and getting them excited about, the engineering phenomenon that they are learning about. Applications that remind them why they choose to become an engineer, especially when the math becomes more abstract. And so here I want to go into some of our software tools, and I've picked out some examples that I think will illustrate how good math tools can help you improve engagement. So I'm just going to, oops. So here I have Maple. I see. So here I have Maple on my screen, and I'm going to make this a little bit bigger. So I really like this example. Now, my background is in electrical engineering, Signal processing is a big part of what I studied. And so when I saw this example, I really liked it because, again, signal processing, a lot of times, when you have to solve for or apply a Fourier transform, or we were looking at different filter design, I didn't always appreciate what I was doing. So in this example, what we're going to look at is hybrid images. So here I have a hybrid image of a cat and a dog. So the high spatial frequency data for the image of the cat is added to the low spatial frequency data from the image of the dog. So you take the cat, you apply a 2D Fourier transform over here, you pass it through a high pass filter, and then you add this with the same procedure for the dog, except the dog has been, the Fourier transform for the dog has been applied to a low pass filter. And so here, what we're trying to get at is when we view objects near us, we see fine detail. So that's higher spatial frequency. And when we view objects at a distance, the broad outline has greater influence. And so the lower spatial frequency dominates. So I'll show you an example here. So here, if I make this really small, hopefully the image of the dog is more prevalent. Similarly, if I make this very large, the image of the cat should be more prevalent. And so what I like about this example here is, you can apply the same principle for any image. And so that's what we've done over here. We've taken advantage, in this case, I'm using Maple. We've loaded some of Maple's image processing and signal processing package. I'm going to go and execute this code over here, and we can just walk through this, and a student can walk through this. So here I'm going to bring in an image of Einstein and Marilyn Monroe. And so here's Einstein, here's Marilyn Monroe. And now what I'm going to do is I'm going to apply a Fourier transform to both images. So I'm just doing that over here. I'm using the software to do all the heavy lifting. And at this point, I want to see what the power spectra of the unfiltered image is. So lower frequency data will be near the center, higher frequency data will be further away. So here is the power spectrum for the Einstein image and for the Monroe. So now we're going to create our filters. So over here, I'm going to define the cutoff frequency for the high and low pass filters. Now I've just picked these values, but of course you can change them. And going to something we'll talk about later on is this, allowing students to experiment. So in any case, here's this. I'm just going to run these. So I'm going to apply it to the low pass filter. The Einstein image, we're going to basically put it through a high pass filter. The Monroe image, we're going to put it through a low pass filter. And now let's look at the power spectra of the filtered images. So here we have it. This is what we would expect. So over here, we don't see that low pass. We don't see the low pass data. And so now we're going to go ahead and combine these images. Oh, before we do that, let's actually go look at the actual images. So here we can see the image. This is Einstein. This is Marilyn Monroe. And now we will go and add the filtered Fourier transform to both images. And here you have it. And so same thing. We can make this smaller. And as I do that, the image of Marilyn Monroe is more prevalent. And similarly, as I make this larger, I should be able to, Albert Einstein's face should become more in focus. So this is one example of, what I mentioned about improving engagement, getting students to understand or appreciate why they're learning a particular concept and why they need to understand the math behind it. Here's another example. So this comes from, it's an application. It was an actual issue that chemical engineer at a paint processing facility ran into. So what happened here was during a routine sample control inspection, you have your quality control engineer identified a discrepancy between the expected and actual concentration of paint produced in a reactor. and the concentration of the paint produced was double the expected value. So here they used Maple to identify and then correct their model based on the actual concentrations of the paint being produced. So what I like about this is it explains, the reason for having a mathematical model in the first place, how one goes ahead and constructs that mathematical model, and then how you can, evaluate the mathematical model against the experimental data and make amendments and changes to that model to better fit what you're seeing. So here we use Maple to go ahead and formulate the reaction kinetics. And so you'll see over here, we define the matrix, we have our function, we have our different variables, auxiliary variables. And so now I'm able to create a system of nonlinear differential algebraic equations. Now, typically solving these equations by hand would be very cumbersome, and you would lose sight of, your end goal, which was to create the mathematical model and then look at the experimental data based in comparison to what the mathematical model is predicting. So here we have our system of differential algebraic equations. We do a little rearranging, and here you have it with your initial conditions. So now we can go and, put in the values for the physical parameters. So here are the parameters in this table and the initial conditions. And so we can go and solve this differential algebraic system using the dsolve command in Maple. So we'll go and do that, and I can get the plots. So this is the model for what the concentration of compound A, our carbon dioxide, and all these other compounds. So now that we have our model, we can go and actually validate our model against experimental data. And so here, the experimental data was captured in an Excel sheet. We could go ahead, pull that in, and then use Maple's commands and programming language to go ahead and overlay the experimental data versus the theoretical model prediction. So we've done that over here. And you'll notice just by looking at this, so the theoretical concentration of C versus the experimental data and that of A is off. And so over here, you can actually do this statistically. So we can go and confirm the presence of error. And actually, once we've done this, we see that the presence of the error is in compound A. So here we have it. Over here, I pulled it out and I've put it into this table. And so we can look at the root mean square error, and we can see very clearly that the compound A is where we've made a mistake. So now we can go ahead and update the reaction kinetics model. So we can do that over here. And so a better prediction of the reaction kinetics of compound A can be obtained by parameterizing the numerical solution for the differential equation and fitting it to the theoretical model of the experimental data. And we're going to use a least squares approach, again, explaining to a student or having them understand why being able to, why you're learning about the least squares approach, why the statistics is important, being able to do that in this type of example. So we've done that over here. We're able to get a new value for this parameter, and we can see that this value is much smaller than the value that was used to develop the model. So 10.9 versus 28.7. And we can go ahead and update our model and compare it to the old model, the new model, and then the experimental data. And we're seeing that we get more accurate results. Again, I'm just picking some examples. So this one is, an example that comes from chemical engineering. The first one was about signal processing. But again, the idea here is to get students to get excited about why they're learning these concepts. So something else I want to point out quickly is that, we have a bunch of applications in Maple. Let me pull them up that you can use. So if I look at over here, you can take any of these. There's some in the natural science, there's engineering applications, and you can look at any of these examples tweak them, customize them to make them your own, and then use this as the motivation behind a particular lecture that you're conducting. Another thing I wanted to point out is our application center. So I love the application center. It's documents that have been created by our user community. And all of these are here for you to, try out, explore, so we can look at all of the different applications, top applications, and you can go and filter them based on what you're trying to show. So let's go back to our presentation over here. So the next thing I want to talk about is, being able to showcase concepts. So if I get this, so we want to help students learn the important concepts by, again, relieving the burden of tedious, error-prone calculations. And we saw some of this in the previous examples. But I want to show you a few more examples where it's very clear that the software will go ahead and do that cumbersome, time-consuming calculations so that the students, again, don't get bogged down in the details of the math. They don't get stuck where did I make a mistake? And so it doesn't actually take up too much class time. The other thing that I think is really important with a good math tool from an engineering perspective is allowing students to visualize and understand what the data or their findings are, the results of their findings. And I think a visualization does a good job of that. So here I'm going to show you a few more examples. And this time I've picked out through. So these examples were done again in MapleFlow. And so I want to show you this particular example. Again, I think I'm biased because I am an electrical engineer. So this was the idea of a worst case circuit analysis with Monte Carlo simulation. And the premise here is that you have a number of components in a circuit and the distribution of their parameters. The issue here is that there's a risk that must be identified and managed and mitigated in the design process because all of the different components have a different level of tolerance. And so the worst case circuit analysis is a set of techniques used to analyze how variations in the parameters influence circuit performance. So here we're going to look at the Monte Carlo analysis. And in this case, parameters are randomly selected from a distribution. And the circuit is simulated anywhere from 1,000 to 100,000 times. And so then given the results, the circuit can be redesigned to minimize failures due to parameter variations. So I'll show you this. So here we have a circuit over here, and you can see that our output voltage is defined by this function. So we have these parameters over here, our components, R1, R2, R3, so on and so forth, our voltage. And so here it is, the number of samples for this particular one, 1,000, but these values can easily be changed. And then I can go and actually use the statistics package to basically perturb all of these different values. So I've done that over here. I can simulate the output voltage, and I'm doing that. And I can look now at the mean and standard deviation of the results. So in MapleFlow, I can just calculate that by clicking equals and enter. It executes everything. Similarly, for the standard deviation, and I can see a histogram of those results. Now, one thing that I really like about MapleLearn over here is, change this a little bit, is I can go and make changes to any of these parameters. So let's say I change this to 900. And I execute, everything is automatically propagated down, and you can see that the curve has automatically changed. So I can go back. Similarly, if I want to clean up my document, so I don't want students to be bogged down by, the commands or the syntax, I want them to be able to focus on the results, I can go ahead and take all of this, and I can go and, here we go, insert a section. And then I can hide this. I didn't click one. Let me do that. Here we go. Insert. section, and I can close this. Oh, I'm making a mistake somewhere. Let me see. So you can put things in sections and collapse it to clean up your document. Let me show you one where I have it already in a section. So here we go. And you'll see over here, move this out of the way. We'll try again. Now I can collapse all of this into a section. If I don't want to see the commands, I can right click, I should say, and say hide command. And so here I have my plot. So that's one example that I wanted to show you. Another one is the analysis of vapor conversion refrigeration cycle. So this one, my colleagues actually recommended it to me. So one of the issues that they talked about is when they were studying, this process at university, often you would have to go ahead and look at these charts in order to get the parameters, and you'd have to make estimates. It would actually take a lot of work in order to get some of the data. And the nice thing here with MapleFlow is that I can go ahead and I have a thermophysical data package where I can pull properties that I want. So over here, the pressure, enthalpy, the temperature chart that I want to use is this one. So I'm going to assign it to a variable. And now I can go ahead and use this package to pull out all of these values. So here is, the value for H1, H2, and the pressure. So this is something I can do. One thing I like about this particular example is looking at it even before we get into the calculation stage. One of the things that I think is interesting is for students to start looking at, and answering the questions, why is the enthalpy H4 equal to that of H3? And starting to have that discussion, making sure that they actually are able to understand that based on what is being taught in the classroom. The other thing here is that MapleFlow is units aware. So I could go and change this at any point to a different unit. And MapleLearn will MapleFlow, I should say, will provide me with the updated result. So here's that calculation of the enthalpy with BTUs per pounds. Similarly, over here, I can go ahead and change this if I wanted to PSI. And here's the new result. So this is another example that I wanted to show you where, again, what we want to do is focus on the concepts and help students learn those concepts that are being taught in the class. There's a bunch of different applications within the application gallery of MapleFlow, and I would encourage any of you to take a look. Again, I picked 2 examples that resonated for me, but there's many over here in all different domains. So at this point, I want to get on to my next topic, which is about, a goal is to encourage experimentation and iterative design. What we want students to do is to be able to see what happens when they change parameters, when they push their design or their model to the limits. And in order to do this, I think what we want to be able to do is give students a platform and software where it's very easy to do that, where it's very easy to change parameters, where it's easy for them to realize that they may have made a mistake and then go ahead and change their model. What we want them to do is even be able to explain or articulate why they chose a certain design and be able to share that with others in their class or with their instructor. And then as they move on into the workforce, be able to have the tools to be able to do this with their employer. So here, I want to show a few other examples. So going back into this Maple Flow. I picked this one because I find it really fun. So this application applies an IIR filter to an audio file. And so here I have my audio file, and I'm just going to go ahead and I will play that for you. So here I have the audio file, and I can go ahead and look at the spectrogram of the original audio signal. I can apply my IR filter. Of course, a student can go ahead and change the cutoff frequency and see how the output, the result of the output. So let me go and play this for you. Give me 1 second. Let me. So here's the files. So here is my input audio. So I'll play that. So that's what we would expect. And this is the output after applying that IR filter. And now we can go ahead and say, well, what happens if we change the cutoff frequency? What happens if we change the type of filter that we're using? So let's go and change the cutoff frequency. And if I've done everything correctly, we should hear the new results. Oh, I picked. Let me see. Let's try it. There we go. It updated. There we go. We can hear it. So that's one example. Again, what I like is that you can change the different types of filters that you can apply. Here's another example that I wanted to show, and this is in Maple. Now this one is slightly different. Here it's looking at a finite impulse response filter. So here, same concept, we're using Maple. We can go ahead and load a different file. So I'm clicking on this button, and I can pick my file that I want to load. So I can do this, open it. I've set this up so everything will just automatically change. So here's the frequency spectrum. Here is the input signal in the time domain, so I can look at that. And then I can look at my finite impulse response filter. I can change the number of elements, the cutoff frequency. I can make this filter. Oops. Let me execute this. Now I should be able to click on make filter. I can view the plot of the filter coefficients if I want to. I can change the start and end times, looks at the number of samples, and then I can go ahead and execute my filter. And I can play the input. So you should have heard that versus the output. And so I can change this again. We can try something different. Let's go ahead and we have this. I can change the number of elements, the cutoff frequencies, and I can go and execute that filter. Actually, this time, let's go ahead and change the type of filter. We can go and look at high pass. Oops. There we go, I made a mistake. We can change this over here. Well, I have to make, there we go. And if I execute the filter,
MapleSim is a tool for.
you should be able to hear that.
MapleSim is a tool for.
So that's another example over here to play with, that your students can play with, and again, understand the concept of this case of a digital filter design. Lastly, I want to talk about how, we want to instill understanding. So I think all of us would agree that we don't want our students to actually just mimic what they see in class to get the right answer. We want them to understand why they're doing what they're doing. And so one of the things with the tools that I'm showing you today, and a good math tool, is, you allow students to provide tools so that they can drive deeper understanding to the mathematics. Being able to allow them to visualize mathematical concepts, break them down into steps, use scaffolding methods to build on existing knowledge. And I think all of these different techniques allows us to drive deeper insight and understanding. So here what I have is some documents that I want to show you, which illustrates this point. So here, actually, I'm going to show you some documents that we have for differential equations. And I picked this because it's an area that I struggled with as an engineering student. I think one of the first things in my first differential equation course where I didn't really understand was this idea that it could have different solutions. So here's an example here where I find this really goes to show this point. So a student can go ahead and play with the values and click on show vector. And so it goes and talks about, here's your direction field. As you change the values for X and Y, you actually get a unique solution, a particular solution. And so they can go and change this again. And what I like about these documents is that there's a sequence to the documents. So here it's a visualization to help students explore, what is a differential equation and how it relates the function and its variables to its derivative. So here we have it. And the idea is that we don't know what y of x is, but we can learn about it from the equation. And now we can look at different examples. So very simple one. And this one is, it explains what the differential equation is, the concept of an order. All of these documents can be modified and changed by the instructor. But I like this because here it tells you, consider this differential equation. What functions satisfy the equation? What functions are equal to their own derivative? And a student can use this and start playing. Maybe they'll try with a x squared. And then hopefully they will realize that it's the exponential function. Similarly, they can look at this one. Same thing, what functions satisfy this differential equation? And they can play with values for x. So hopefully they'll be able to see what the solution is. And at any point, if they get stuck, they can always click and see solutions. And they can look at it. Here's another example where now we start to introduce the concept of initial conditions. So here I can make this a little bit larger. So this shows me my particular solution, and I can visualize this. As I change the values, in this case of A and B, my parameters, I can see how the particular solution changes, and I have reference to that, that differential field over here, the vector field. And so I can change this. And now I can start getting into the concept of how to actually solve the differential equations, and I can start looking at these. So this is one of the technique to actually solve for separable differential equations. So that's one thing that I wanted to show you over here, is just using the different tools, how you can create lessons that break down a concept into smaller pieces, but still allow students to explore and to play with different values. And ultimately giving students the ability, in this case, to practice. So this one I wanted to show you here is, it gives you steps, but the idea is here a student can go and change that differential equation. So let's say they could do it on paper, but if they ever get stuck, they can go and show the steps. And they can look at the steps for it and make sure that they got the same answer or start to identify where they have made a mistake. So I'm going to conclude this presentation because I want to give us enough time for questions or comments. Is just to talk about, our goal. So at MapleSoft, we believe that mathematics improves our lives and makes us safer, more efficient, and more innovative. And I think without mathematics, we wouldn't be where we are today. And so that's why I and the development team are really passionate about helping students, researchers, engineers, and scientists take advantage of the power of math to enrich the world we live in. So, at MapleSoft, we believe that math matters, and we're proud of having an impact on the world around us. So today in this presentation, I showcase several different products from our MapleSoft Mathematics Suite. So I showcased Maple, Maple Learn, Maple Flow, and the Maple Calculator. And so, all of these products they're available both desktop, mobile, and online solutions, and they cover math or engineering topics from high school all the way up to graduate school and beyond. So just a summary, we have Maple over here. So Maple, most powerful and comprehensive environment for exploring, visualizing, and solving even the most difficult math problems. Maple has a rich programming language that you can use, and you saw parts of it as I went through this presentation. We have Maple Flow. So this is a fairly new tool, and it's a tool for engineers to brainstorm, develop, and document their design calculations. Lots of different applications in this area. So I showed you Maple Learn briefly, and it's an interactive online environment for exploring concepts, solving problems, and creating and sharing rich hands-on content. And then I didn't showcase, but here's the Maple Calculator. It is a mobile app that allows you to take a picture of your math and will give you results as well as step-by-step solutions. It has an editor, so you can actually enter in your values, as you can see in this video over here. It'll actually give you solution steps, and it supports 3D visualizations as well. One of the nice things about all of these products is that they are developed with the Maple math engine underneath. So anything you can do in Maple can be done in any of these products. And lastly, and so I just want to kind of conclude, if you're not sure about which product to use, if you're interested in trying them out, if you want a demonstration of any of these products, feel free to get in touch with us and contact us. You can go to our website, maplesoft.com/suite. There's a form in there, and you can reach out to us and ask us any questions to get detail about any of these products. And depending on your students' need, the needs of your institution, the level, we have people using 1, 2, or all 4 of the products.